Hello everyone, welcome to new class. Today I am going to discuss about electromagnetic induction. A British scientist, Michael Faraday, discovered the phenomenon of electromagnetic induction. After a variety of experiments, he found that a moving magnetic field does give rise to an EMF. Most commercial apparatus like motors, generators, and transformers are based upon the principle of electromagnetic induction. Faraday's laws of electromagnetic induction. There are two laws. First law states that whenever there is a change in magnetic flux linked with a coil, an EMF is induced in it. Or we can say whenever a conductor cuts magnetic flux, an EMF is induced in that conductor. Faraday's second law. This law states that the magnitude of the induced EMF is equal to the rate of change of magnetic flux linking with the circuit. Let N be the number of turns in the coil, Phi1 be the initial flux, Phi2 be the final flux linked in Weber. Then the induced EMF E is given by minus N into d phi by dt volts. The negative sign he is explained with the help of Lenz's law. Lenz's law states that the direction of the induced current is such that it opposes the very cause which produces it. From the first law, we know that if there is a change in magnetic flux linked with a coil, an EMF is induced in it, and if there is a closed path, then a current will be flowing in that circuit. And the direction of that current is given by the Lenz's law. Let us go through a simple problem. A flux of milliweber linked with a coil of 100 turns is reversed in 0.5 second. What is the value of induced EMF? We know induced EMF is equal to N into d phi by dt. N is the number of turns and is given 100. And we have to find d phi by dt. That is the change in flux. For that we have initial flux Phi1 is equal to 1 milliweber, that is 1 into 10 raised to minus 3 Weber. And we know it is reversed in 0.5 second. That is we have the final flux Phi2 is equal to minus 1 into 10 raised to minus 3 Weber. So substitute these values, that is N into Phi1 minus Phi2 divided by T. T is given as 0.5 second. Here we can write either Phi1 minus Phi2 or Phi2 minus Phi1. That is 100 into 1 into 10 raised to minus 3 minus 1 into 10 raised to minus 3 divided by 0.5, and we get 0.4 volt. If we write Phi2 minus Phi1, we get here minus 0.4 volt. Now let us go through the electromagnetically induced EMF, or simply the induced EMF. There are two types of induced EMF, that is dynamically induced EMF and statically induced EMF. The EMF induced in a coil due to the relative motion of the conductor within a stationary magnetic field is called dynamically induced EMF. That is, in this case, the conductor is moving and the magnetic field is stationary. Example, DC generator. The EMF induced in a coil due to the change of flux linked with it, or change of flux is by the increase or decrease in current and is called statically induced EMF. That is, here the conductor is stationary and the flux is changing. Example, transformer. Let us find the magnitude of dynamically induced EMF. Consider a conductor of length L meter lying within a uniform magnetic field of flux density B Weber per meter square. Let it move through a distance dx in time dt. Then the area swept by the conductor is given by L into dx. And flux cut by the conductor is flux density into area, that is B into L into dx. And according to Faraday's law, the induced EMF is given by the rate of change of flux linkages, that is B into L into dx by dt. And we know dx by dt is velocity of the conductor, that is BLV volts. And if the conductor moves at an angle theta to the direction of the flux, then we have induced EMF is equal to BLV sin theta volts. Now let us go through the magnitude of statically induced EMF. And there are two types of statically induced EMF, that is self-induced EMF and mutually induced EMF. Then what is the difference between self-induced EMF and mutually induced EMF? Let us go through self-induced EMF. The EMF induced in a coil due to the change of its own flux linked with it is called self-induced EMF. Consider this circuit. As the current in the coil changes due to the change in applied voltage, flux linking with the coil also changes, producing an EMF. This EMF is called self-induced EMF. As per Lenz's law, the direction of induced EMF is such as to oppose any change in flux, that is opposite to the flux producing it. Hence, often it is referred to as counter EMF or self-induction. The property of the coil which opposes any change of current or flux through it is called its self-inductance or inductance and is denoted by L. And the magnitude of self-induced EMF is given by E is equal to minus L into di by dt, where L is the self-inductance or simply inductance. Also, we know that induced EMF is equal to minus N into d phi by dt. By comparing these two equations and after integrating, we get the value of self-inductance L is equal to N into phi divided by I. And we know MMF is equal to phi into S. From this, we get phi by I is equal to N by S and substitute the value of phi by I here. We get L is equal to N square by S. So, there are different expressions for the self-inductance, that is E is equal to minus L into di by dt. Also self-inductance L is equal to N into phi divided by I and N square by S. The unit of self-inductance is Henry. Now let us go through the mutually induced EMF. The EMF induced in a coil due to the change in current in the neighboring coil is called mutually induced EMF. Consider two coils P and S close to each other. Then any change of current in coil P result in mutually induced EMF in coil S. Thus, the two coils are mutually coupled. Any change in current I1 of coil P causes flux, the change in flux to link with both the coils. The EMF induced in coil P forms the self-induced EMF, while the EMF induced in coil S forms the mutually induced EMF. Coil in which change in current takes place is called primary. That is, P is for primary, while the other is called secondary. S is for secondary. Next is mutual inductance. The mutual inductance between the two coils is the property by which change of current in one coil induces voltage in the other coil. And the value of mutually induced EMF E2. E2 is given by minus M into dI1 by dt. That is, the induced EMF in the secondary coil is due to the change in current in the primary. And also we have the mutual inductance M equal to N2 phi divided by I1. That is, mutual inductance is in the secondary coil due to the change in current. Or if the supply is in the secondary coil, then the mutual inductance will be in the primary coil. So in that case, we can write N1 phi divided by I2. And also there is another expression for mutual inductance, that is N1 N2 divided by S, where S is the reluctance. M is called mutual inductance or coefficient of mutual induction, and the unit is Henry. Mutual inductance in terms of coefficient of coupling is M is equal to K into root of L1 L2, where K is the coefficient of coupling. L1 and L2 are the self-inductance of first and second coil respectively. When K equal to 1, the coils are said to be tightly coupled, and when K equal to 0, the coils are magnetically isolated from each other. Normally the value of K is less than or equal to 1. Thank you for watching the video. If you like the classes, please like, share and also subscribe my channel.